Good morning, all of you. So we were discussing with the chapter Mechanics of Fluids, and in the last class we discussed Stokes' law, right? So Stokes' law actually gives an expression for the dragging force. So the dragging force means as when an object is placed inside a fluid, it will experience a force of friction, isn't it? For example, if you are considering a cylinder like this, which is filled with fluid, okay, now you are dropping a spherical ball inside this cylinder filled with fluid. At that time, what will happen? When it moves inside the liquid, surely it will experience a dragging force. That means a backward dragging force. And you got an expression for the Stokes' law, which is given by F is equal to 6 pi eta RV. From this, it is clear that since 6 pi and eta is the coefficient of viscosity, so both are constants. So F is proportional to the radius of the sphere and F is proportional to velocity of the sphere. That means if I am increasing the velocity of this sphere, or if the velocity of the sphere as it moves downwards, if it is increasing, the viscous force also increases. Okay, and if you are using a larger sphere, the viscous force again increases. Understood? So this is actually the Stokes' law of viscosity that you know. Now today we are moving to the one of the important topic in this chapter, which is again related to this Stokes' law, that is terminal velocity. Terminal velocity. Okay. So actually when we discuss the term Stokes' law, we usually use the example of raindrop. Raindrop is considered as a spherical body, and if it is having a radius and it is moving with a velocity v, we can use that example in the case of this terminal velocity also. That is, if there is an example like the falling of a raindrop, okay, raindrop in air, you consider the raindrop in air. So we have studied friction in various cases, like solid friction, that is over a surface. If a body is moving, it has friction. Again, in air also it has friction. Then in fluids or in liquids you have friction. Air, you know, aeroplanes are having a peculiar shape in order to reduce the friction, air friction. Okay, like that if you are moving in liquids, you feel it very difficult to move faster as you are moving normal case, isn't it? Why? Because there is a drag by the fluids, that is fluid friction. Likewise, friction is there everywhere, air, liquid or surface, solid surface, everywhere it is there. So when we are considering a raindrop in air, you know, in the case of any object, when it moves downwards, starting because of gravity, its velocity will be larger or higher. Okay, so in such a case, first initially the raindrop will move faster. It accelerates due to gravity, isn't it? So if you are considering a raindrop, now raindrop is in air. Okay, now first the raindrop moves with larger velocity because it accelerates because of gravity. Okay, now when it comes downwards, surely because of the drag or the friction by the air, it experiences a drag. That is, we call it as the viscous force, isn't it? So when it comes down, what will happen? The force of viscosity will be acting in which direction? As in this direction, isn't it? Force of viscosity will be acting like this in order to oppose the motion. Clear? So we already understood that if the velocity is increasing, the force of viscosity also increasing, isn't it? So let the body moving with a velocity, similar to that the force of viscosity also increases. Or in addition to this force of viscosity, another force is also acting. What is that? As it is the upthrust. You may have studied in your 9th standard, that is buoyancy. Buoyancy or upthrust means it is the force acting in the upward direction towards the body or the object falling in a liquid. Understood? So liquid or fluid, okay, air or liquid, water can be considered as fluids. So here also two forces are acting in the upward direction. What are they? Yes, first one is the upthrust or the buoyancy, and second one is the viscous force. Okay, now again the body is moving like this. So body has a weight which is acting in the downward direction. So this is the weight of the body, then which we can call it as mg. Mg you have studied, the weight of the body. Then two forces are acting in the upward direction. That two forces are, first one is upthrust or buoyancy, and second one is the viscous force, which is given by Stokes law. Clear for you. Now, then after some time, a stage is reached when the weight of this body becomes just equal to the sum of upthrust and viscous force. Okay. So, after some time, when the body is moving downwards, after some time, the weight of the body becomes equal to the two forces acting in the upward direction. That is, weight is acting downwards and this is acting in the upward direction. At that time, what will happen? As if these two are equal. That means here there are two forces in the upward direction and W equal to mg acting in the downward direction. So when these two has a sum and it must be equal to the weight. Understood? In such a case, what will happen? As the body begins to fall with a constant velocity. That means acceleration becomes zero. If it is having a constant velocity, means acceleration is zero. So the body begins to fall with a constant velocity, and that constant velocity or that maximum constant velocity acquired by a body while falling through a viscous fluid is called its terminal velocity. Understood? What do you mean by terminal velocity? Is when the weight of the body is equal to the sum of upthrust and viscous force which is acting in the upward direction. What will happen? The body acquire a constant velocity. At that time, acceleration is not there. So that constant, from that point onwards, it will move with that constant velocity. So such a constant velocity acquired by the body when falling through a viscous fluid is known as its terminal velocity. Okay, so how can you define terminal velocity? Okay, the maximum constant velocity acquired by a body while falling through a viscous fluid. That is known as what? Terminal velocity. Understood? So, I am considering a sphere like this. In our first figure, a sphere like this. And suppose the sphere has a density rho. Density of the sphere is rho. Falls through a liquid. Okay. And the liquid has a density sigma. Understood? Now, what is the condition? Yes, the condition is when this sphere acquire a terminal velocity, the weight of the sphere must be equal to the sum of upthrust and viscous force. Isn't it? So, first we will write the expression for upthrust. That is, upthrust is actually, you have studied the Archimedes principle. So what is upthrust here? Upthrust is actually equal to the weight of the fluid displaced. That is, when a body is placed in water or in a fluid, the amount of fluid displaced or amount of liquid displaced is actually equal to weight of the body, isn't it? That is what given by Archimedes principle, and from that you can say that the upthrust is actually equal to the weight of the fluid displaced. Okay, that is m into g. Clear? Now what is m? M is the mass. In terms of density, how can you write? You know, density is equal to mass by volume. Isn't it? Density is equal to mass by volume. Okay. Now from this, what is mass? Mass is equal to density into volume. Here we are considering the density or the weight of the fluid. So this density, you know, the term is sigma. Here we have mentioned that the liquid has a density sigma. So how can you write? Sigma into volume. Understood? Now what about the oleum? Oleum is equal to sigma into 4 by 3 pi r cube. That is the oleum. Okay, 4 by 3 pi r cube sigma. Now substituting here, it will be 4 by 3 pi r cube sigma into g. Clear? Now the force of viscosity, what is the expression? Is by Stokes law, we have the expression for force of viscosity, that is F is equal to 6 pi eta r v, isn't it? Okay, where r is the radius of the sphere and v is the velocity. So F equal to 6 pi eta r v. Okay, so we got both the upward forces acting in the upward direction, right? Now we have to find the expression for weight of the body acting downwards, that is weight of the body is given as weight of the spherical body, okay, is equal to again m into g, isn't it? So here what is m? M is again in terms of density and oleum. You can write 4 by 3 pi r cube rho, because here rho is the density of the body. 4 by 3 pi r cube into rho g. Clear for you? Now we can substitute. So the equation will turn to, that is the upward forces, sum of the upward forces 4 by 3 pi r cube sigma g plus 6 pi eta r v is equal to 4 by 3 pi r cube rho g. Clear? So what is 6 pi eta r v? Yes, it is 4 by 3 pi r cube g into common, no? So rho minus sigma, isn't it? So from this, what is this velocity? Yes, this velocity is given as v is equal to 4 by 3 pi r cube g divided by 6 pi eta r into rho minus sigma. Clear? So here we can see that the pi terms will get cancelled. Pi terms will get cancelled, and then in terms of 2, this is 2 and this is 3. Okay, r and r cube will get cancelled, so it will become r squared and g then eta. So we can rewrite the expression as 2 by 9 r square rho minus sigma into g by eta. Okay, 2 by 9 r squared rho minus sigma into g by eta, where rho is the, what is rho? Yes, rho is the density of sphere and sigma is the density of the liquid on which it is falling. G is acceleration due to gravity, r is the radius of the spherical body, then eta is the coefficient of viscosity of fluid, and finally v is the terminal velocity. Understood? So this is the expression for terminal velocity. Hope you understood. Now we are moving to the next topic. Okay. So our next topic is surface tension. We have studied one of the property of fluid, that is viscosity, and we studied all the details regarding viscosity. Now we are moving to surface tension. Okay, this is also very important. For this I am taking an example of a steel needle. Okay, suppose you are considering a steel needle, and you may have seen that the steel needle can float on water. Even though it is more, steel is more dense than water, the steel needle can float on water. Okay, so why is this so? As this is because the water surface will act like a stretched membrane. Stretched elastic membrane and supports the needle. Understand? That means the surface, the liquid on the surface of the water surface always tends to occupy a minimum surface area and it will behave like stretched membrane. Understood? That is, they will behave like an elastic membrane which tends to occupy a minimum surface area. You may have seen small insects floating on water. That is because of surface tension. Okay, that is the surface here. The surface of the water will behave like a stretched membrane. That is, they will tend to occupy a minimum surface area. So, there will be a stretching and that particular insect or that particular needle can stand in that membrane. Understood? Can hold there. So, that is what called surface tension. One example I will say, that is the raindrops or drops of mercury. They when placed on the glass plate, they will occupy the shape like spherical shape, isn't it? That is, the raindrops and drops of mercury placed on the glass plate can be seen in the spherical shape. Why so? Because when suppose the liquid is like this, okay, liquid falls here, but they will occupy like this. They will tend to reduce the area, okay, tend to occupy a minimum surface area. So, in order to reduce the minimum surface area, they have to be spherical enough, isn't it? So, so many examples are there like which obeys the surface tension. Understood? So, surface tension, how can you define? As it is the property of a liquid by which the liquid surface will tends to occupy a minimum surface area and they will behave like a stretched elastic membrane. Understood? It will occupy a minimum surface area and they will behave like a stretched elastic membrane. Okay. Now we can find an expression for this surface tension. For that, I am considering a liquid on a beaker. Let this is our beaker. Clear? So we are considering the surface over here. Now in this surface, we are considering a small element like a line element like AB. So this is a small line element that I have considered on this surface. Okay. Now here the line element is actually in equilibrium. The liquid is at rest. Now this line element is in equilibrium. Means each element on this line is at equilibrium because they are acted upon by equal and opposite forces like this. Understood? Here F, here also F. So equal and opposite forces are acted upon on this line element. That means this force will act perpendicular to the line element AB. Understood? The equal and opposite forces will act perpendicular to the line from either side as shown in the figure. So, the forces acting on this line is proportional to the length of the line. That is the first point. The forces acting on this line is proportional to the length of the line. Understood? If L is the length of this imaginary line and F is the total force on either side, you can write F is proportional to L. That is, the constant can be changed. That is, F is equal to S into L. So, what is this S? S equal to F by L. Now, this S, we can call it as the surface tension. Okay, once again we are considering the surface of a water which is at rest now. Now in this surface I am considering a line element. So this is the line AB and this is an imaginary line. Okay. Now each element of this line is acted upon by the forces, equal and opposite forces, which is perpendicular to it. That is why this line is in equilibrium. Understood? Now for finding an expression, I can say that the force which is acting perpendicular to this line is proportional. The force is proportional to length of the line. That means if I am extending the line, if the length is increased, the line element has a length which is greater than this, the force is also increasing. So if the length is increasing, the force is also increasing, which means that F is proportional to L, and F is equal to S into L, S equal to F by L. From this expression also, we can define surface tension. Generally, surface tension means it's the property of the liquid which tends to occupy a minimum surface area, and it will behave like a stretched elastic membrane. Now, from this equation, you can define surface tension as the force acting per unit length of an imaginary line drawn on the liquid surface What about the direction? As the direction of force being perpendicular to this line and tangential to the liquid surface. Okay, so this is also another definition for surface tension, that is the force acting per unit length of an imaginary line drawn on the liquid surface, the direction of force being perpendicular to this line and tangential to the liquid surface. That is also known as the surface tension. So it is denoted by the letter S, and surface tension is a scalar quantity. Understood? Surface tension is a scalar quantity. Now what about the unit? From the equation you know S equal to F by L. The force has the unit Newton and L has the unit meter. So the unit of surface tension is taken as Newton per meter. Unit is Newton per meter, and in C, this is SI unit. If it is in CGS, you can write it as dyne per centimeter. Clear? Now what about the dimension? Dimension is equal to force by length. Clear? Force by length. Dimension. So F has the dimension mLT raised to minus 2 and length is L. So again T raised to minus 2. This is the dimension for surface tension. Clear? Dimension for surface tension. Okay, now what are the factors affecting surface tension? Let us have a check. So one of the factors affecting surface tension is temperature. Okay, so how this temperature affects surface tension? As the surface tension decreases. Surface tension decreases with increase in temperature. Understood? Surface tension decreases with increase in temperature, or vice versa you can say surface tension increases with decrease in temperature. Clear? I will say one example. This when we taste hot soup, okay, hot soup, it has very good taste than cold soup. Okay, hot soup tastes better than cold soup because hot soup means there the temperature is increased, so surface tension decreases. So surface tension decreases means what? It can spread. The hot soup can spread over a large area, isn't it? If the surface tension is more, it will always have a tendency to minimize the area, to occupy a minimum area. Understood? So when we are using hot soup, it can spread over a larger area so that we can taste better than a cold soup. Clear? So one of the factors affecting surface tension is temperature, that is inversely proportional. Surface tension decreases as the temperature increases. Okay. Now the second factor affecting surface tension is addition of impurities. Addition of impurities. That means the surface tension of the liquids changes appreciably with addition of impurities. That is, for example, a highly soluble substance like sodium chloride. Okay, sodium chloride is highly soluble, so it will increase the surface tension. The surface tension is increased. Surface tension of water can be increased by adding sodium chloride. Suppose if you are using a sparingly soluble substance like phenol or soap or something like that, what will happen is it will reduce the surface tension. Reduces the surface tension of water. So these are all examples for adding impurities and affecting surface tension. Okay. So one of the important question from this section is how the detergents affect surface tension. Detergent and surface tension. That is, surface tension has a wide application in our daily life, and you know detergents, in addition to washing with simply water, we will use detergents also, isn't it? So many detergents are available now. So we will use detergents also in order to remove the dirt from the clothes. So why we are using detergents, or how these detergents change the dirt, remove the dirt from the clothes? That is, when we are using water, water cannot wet the oil stain and all on your clothes, and it cannot remove the dirt completely from the clothes simply using water. But when we are using the detergent, the molecule of detergent can get attached with water and dirt molecules, and they take away the dirt with them when we wash the clothes with detergent. Understood? Why? Because of surface tension. How? Yes, by adding detergents, the surface tension can be reduced. Okay, so detergents reduce the surface tension. That means what? Is when the surface tension is reduced, it can spread over a larger area so that it can make bonds with the oil, dirt and all. Okay, stain and all, and it can go through it easily. Understood? That is why detergents are preferred for cleaning clothes. Okay. So many applications are there for surface tension. As I told, raindrops and drops of mercury, when we place it on glass plate, they have the shape of a sphere. They have spherical shape. Then when you dip a shaving brush or a painting brush in water, what will happen is when you take it out, you can see that the bristles are all stick together. Why? Because they always have a tendency to occupy the minimum area. Okay. Then oil drop can spread on cold water, but it does not change its shape on hot water. So these are all applications of surface tension. Clear for you? So in the next class, we'll discuss the balance of this topic. So today I am winding up the class, and have a nice day. Thank you.